Testing, can you hear me? Testing, can you hear me? Testing one last time. All right, this video is public now, so I'm going to be learning about computer architecture again. I'm going to be reading this book and I'm going to read from where I last left off. So last time I learned about multiplying integers. The last algorithm we talked about, I forgot the name. What was it? Yeah, I discussed it over here in the last stream. Iterative multiplier. Is that what it's called? Wait, let me see. Booth multiplier. Think this is it, yeah. Booth multiplier. Oh yeah, they check for a runs of ones, like 0, 0, 0, 1, 1, 1, 1. They check like a sequence of, they find a sequence of ones. So they save time like that. Anyways, I'm going to be learning about division this time. And yeah, so let us now look at integer divisions. Unfortunately, unlike addition, subtraction, and multiplication, division is significantly slower process. Any division operation can be represented as follows. N is equal to dq plus r. Here n is the dividend, d is the divisor, q is the quotient, and r is the remainder. Okay, wait. Division algorithms assume that the divisor and dividend are positive. The divisor d and the dividend are positive, n and d. The process of division needs to satisfy the following properties. Property 1, r is less than d and r is more than or equal to 0. Q is the largest positive integer that satisfies the equation 8.15. Okay. If we wish to divide negative numbers, then we need to first convert them to positive numbers. Perform the division, then adjust the sign of the quotient and the remainder. Some architectures try to ensure that the remainder is always positive. In this case, it is necessary to decrement the quotient by 1. And add the divisor to the remainder to make it positive. Let us focus on the core problem, which is to divide two n-bit positive numbers. Most significant bit is the sign bit, which is 0. Now dq is equal to dqi 2 to the power of I minus 1. Or dq in binary is like, it's represented like this in decimal. I think that's what they're saying. We can thus write n is equal to dq plus r. dq1 all the way from 1 to n minus 1 plus dqn is equal to 2 to the power of n minus, dqn 2 to the power of n minus 1 plus r. Hold on, what are they doing? And then they use dq1 all the way till n minus 1 plus r. And then they now have this new n and the new q. Wait, I want to see what they're doing over here. What is this? qi 2 to the power of I minus 1. The original problem was to divide n by d. We reduce the problem. The reduced problem is to divide mu n, which is equal to n minus d q n 2 to the power of n minus 1 by d. The remainder for both the problems is the same. The quotient q nu q for the reduced problem has the same least significant n minus 1 bits as the original quotient q. The nth bit of q apostrophe is 0. To create the reduced problem, it is necessary to find qn. We can try out both the choices 0 and 1. We first try 1. If n minus d 2 to the power of n minus 1 is more than or equal to 0, then qn is equal to 1. Otherwise, it is 0. Okay. Once we have created the reduced problem, we can proceed to further reduce the problem till we have computed all the quotient bits. Ultimately, the divide will be equal to the remainder r and we will be done. Let us now illustrate an example that precisely follows the procedure that we have just outlined. Divisor d u minus d. We keep subtracting until like the subtraction gives us less than 0. I think. Let us consider a similar step up as the iterative multiplier to divide two 32-bit numbers. The divisor is stored in a 32-bit register called D. We have a 33-bit register U and a 32-bit register V. If we left shift U and V, then we have value shifted out of V. Then the value shifted out of V is shifted into U. U is initialized to 0 and V is initialized to hold the dividend. We know that the size of U is equal to 33 bits to avoid overflows, similar to the case of the iterative multiplier. So divisor in D, dividend in U, and dividend in V, and U is equal to 0. Divisor in V. U contains the remainder, lower 32 bits, and V contains the quotient. Wait, let me see. Subtracted, and then you do a left shift, U minus D, and then a left shift. Hold on. I think an example like we had for the multiplication, I need to see an example for division as well. Okay, wait. 1, 1, 2, 4, 8. Yeah, this was 13 and 9. Maybe I need something else. Maybe I need, what should we try? 7 divided by 3 with remainder 1. Hold on. Should we do 16 divided by 3? 16 or 17 divided by 3? Wait. Should I do 17 divided by 3? Seventeen. Okay, so what there's, okay, let's try this. Then 17 is equal to 3. Quotient is 5, right? 3 times 5 is 15 plus 2, 17. So we should get this in here. We should get you should get these two. So what they're saying is to store it in V. First we store, what do we store in V? So dividend in V, divisor in D. D is the divisor, V is the dividend. So first step is the dividend. This is V. Hold on. This is V. This is U. And the divisor is 1, 1, 0, 0, 0. So let's see. What they're saying is U is equal to 0. U contains the remainder. P contains, okay. So we left shift. How will we end up with 2 then? Left shift. Left shift. Okay, let's perform a left shift. A left shift. Hold on. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then we do this minus this. This is not positive 17. This is 3. Divisor. We U is equal to U minus D. If U is more than equal to 0, then Q is equal to 1. else u is u plus t and q is 0. Set the quotient bit. So we are doing this minus this, right? Hold on, let me think about this. This is minus 3, right? Minus 16 plus 8 plus 4 plus. No, wait. No. For 2's complement, we flip the bit, right? And then we add 1 at the end. Minus 16 plus 8 plus 4 and plus 1. Yeah. So it's like this. But then what do we do with this? U minus v? U minus d? Minus 16 plus 8 plus 4 plus 2. Is this correct? 1 minus 3. Yeah. I assume. Yeah, it's correct. U minus d. We store u minus d over here. One, two, three, four, 5. Minus d. If u is more than 0, then q is equal to 1. Else, we have q is equal to 0. Well, I mean, q. Where did this q come from? No, if u is more than 0, q is like a random variable inside the algorithm, right? Quotient bit. Well, q is less than 0, so u is equal to u plus d. Wouldn't this just reverse what this is doing? 1, 2, 3, 4, 5. I think, okay, if we end up with a negative, then we undo it. Wait, let's try this. Shift it to the left. One more time. 0 here. Nothing here. -3. So this -3 will give us a negative, so nothing should happen, right? Shift. I don't know if I'm right. 1, 2, 3, 4, 5. So 4 -3 is 1. 4 -3 is 1. 4 -3 is 1. Which is more than 0. And then the least significant bit is set to 1. Hold on, let me think about this. Least significant bit is set to 1. So if this get left shifted one more time, so 1 0 is here, this is 2. Nothing happens. Left shift. Bring 1 here. 1, 2, 3, 4, 5. This gets deleted. Well, now let's try this again. So we have the divisor, which is +3. We have u and v. So v initially contains the dividend, which is 17. So let's say the split is over here. So dividend is 17, but this is a signed bit. 16. You know what? Let's just add a 0 at the end. So 1, 2, 3, 4, 5. There are 6 bits, 6-bit integer. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So initially it's 1, 1, 1, 0, 0, 0, 1, 0. One, two, three, 4, 5. Let's add a 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. in this entire thing, we have V over here, which is the dividend. Dividend into V, U as 0, and then shift it. We shift it, right? We shift, oops. We shifted one position. This gets out. We do minus U is equal to U minus T. But if we end up with a negative, we will add it back again. So uh 1, 2, 3, 4, 5, 6. I think this is 2's question. So this plus minus 3 gives us a negative. So nothing will happen to U, right? Then we right shift it again. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. So 1 minus 1 plus minus 3. Well, we get a negative, so nothing will happen. So we shift it again, right? Let's see. 2 minus 3, negative again. Hold on. I think the next one will be different. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay. So we have 4 minus 3, which is 1. 1 is over here now. 2, 3, 4, 5, 6. 1. And then this is set to 1, right? This is less than this, minus 3 is negative, so nothing happens. I think this is the last step. There should be 6 changes in total. Wait, something is definitely missing. If it's positive, then 1 at the end. What am I missing? To start out, we iterate 32 times for each bit of the dividend. Let us consider the first iteration of the value. At the beginning, the value of the combined register UV is equal to the dividend N. First step is to shift UV by 1 position, line 4. I don't know where I'm making a mistake. So we have positive 17. 1, 2, 3, 4, 5, 6. You have the boundary over here. And then we have 1, 2, 3, 4, 5, 6. So first step is to shift it by 1. Shift the entire thing by 1. Okay, so this gets deleted. Then we shift the entire thing by 1. So 1, 2, 3, 4, 5, 6. Okay. I think it's easier if I have like a large gray line. Do 3, 4, 5, 6. And then since the dividend is originally noted into B, we are shifting the dividend to the left by 1 position. Next step is to subtract the divisor from register U in line 5. Subtract the divisor. So the divisor is 3, minus 3 is this over here. Subtract the divisor from register U. U minus D is 0. Then we set the most significant bit of the quotient to 1. Wait, where do they do that? Where do they set the most significant bit of the quotient to 1? This over here says least significant bit. Otherwise, we add D back to U and we set the most significant bit of the quotient to 0. What? Wait, here it says least significant bit. Is that a mistake? Most significant bit. Set the quotient bit. So wait. Um, 0 minus 3 is minus 3. So it's less than 0. It's a negative. Set the most significant bit. So nothing happens. So we do the shifting again. Shift. Then we get rid of this. 1, 2, 3, 4, 5. Hold on. Can we get rid of this? It doesn't make a difference. Anyways, we shift it again. And then what? We shift it. And then we repeat, right? Shift by 1, U minus D. U minus D would be 0 again. But I should add a line just in case to mark the starting position. Anyways, you shift, correct. Okay, let's try shifting again. 1 minus 3 is a negative, so nothing happens. We shift it again. 2 minus 3 is a negative, so nothing happens, right? Um, One, two, three, four, five, six, 1, 2, 3, 4, 5, 6. Okay, then we shift it again. We end up with what do we end up with? Four minus 3 is 1. 4 minus 3 is 1. 4 minus 3 is 1. So this gets set to 1. This gets set to 1. 1, 2, 3, 4, 5, 6. But then what happens here? The MSB of the quotient to 1. Set the MSB of the quotient to 1. Do they mean this over here, this bit? Do I set this bit to 1? Most significant bit to 1. V contains the quotient. U contains the remainder. If I do this, what happens? Let's see. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Nothing happens. Nothing happens here, so I need to shift it one last time. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. But this over here is 5, right? 5 minus 3 is positive 2. It's positive. This becomes 2. 1, 2, 3. 1, 2, 3, 1, 2, 3. And then this here becomes 1. This is the quotient which is correct. This is the remainder which is correct. So yeah, I think this last bit changes to 1. But why are they saying most significant bit? Shouldn't it be least significant bit? We use equation 8.16 to reduce the problem in every iteration. Equation 8.16 states that the new dividend is equal to this. Here n is the most significant bit of the quotient here. The divisor and remainder stay the same. The last n minus 1 bits of the new quotient match those of the old quotient. We wish to prove that the value of UV at the end of the first iteration is equal to 2n apostrophe such that we can reduce the problem according to equation 8.16. Let us consider the value stored in UV. Just after exceeding 9.4, it contains twice the dividend because we shifted UV by 1 position to the left. Now we are subtracting d from the upper n bits of uv. In effect, we are subtracting 2 in d. Hence, after line 5, uv contains uv minus 2 in d. We have 2 times n minus 2 in minus 1 to the power of n minus 1d. Subsequently, we test the sign of u minus d in line 6. If u minus d is positive or 0, then it means uv is greater than 2 to the power of nd because v is greater than or equal to u, greater than or equal to 0. If u minus d is negative, then u is plus delta is equal to d, where delta is more than or equal to 1. We have uv minus 2 to the power of nd is equal to 2 to the power of nu plus v minus 2 to the power of nd. So u minus d is 2 to the power of n. Okay, plus v, then v minus delta times 2 to the power of n. Hence, v is less than 2 to the power of n. Hence, v is less than delta times 2 to the power of n. Thus, uv minus 2 to the power of nd is negative. We thus observe that the sign of u minus d is the same as the sign of uv minus 2 to the power of nd, which is the same as the sign of n minus 2 to the power of n minus 1d. Now, for reducing the problem, if we observe that u minus d is more than or equal to 0, then n minus 2 to the power of n minus 1d is equal to or greater than 0. Hence, we can set qn to 1, set the new dividend to n apostrophe n minus 2 to the power of n minus 1 d qn. And also conclude that at the end of the iteration, uv contains 2 n apostrophe. If u minus d is less than 0, we cannot set qn to 1. New n apostrophe will become negative. Hence, the algorithm sets qn to 0. In line 11, it adds d back to u. Value of uv is thus equal to 2n. Since qn is equal to 0, we have n is equal to n apostrophe. In both cases, the value of uv at the end of the iteration is 2n apostrophe. We thus conclude that in the first iteration, the most significant bit of the quotient is computed correctly. And the value of uv, ignoring the quotient bit, is equal to 2n apostrophe. In the next iteration, we can use exactly the same procedure to prove that the value of uv is equal to 4n apostrophe. Ultimately, after 32 iterations, we will contain the entire quotient. The value of uv at that point will be 2 to the power of n times n to the power of 32. Here, ni is a reduced dividend after the ith iteration. We have the following relation according to equation 8.17. Hence, u will contain the value of the remainder and v will contain the quotient. There are n iterations of the for loop. Each iteration does one subtraction in line 5 and maybe one addition in line 10. The rest of the operation can be done in O1 time. Thus, per iteration, it takes O log n time. Hence, the total time complexity is O n log n. Divide two 4-bit numbers. 7 which is like this, 4 which is like this, using restoring division. Answer. So uv, you have unknown, you have left shifted. End of the iteration. This is still 0 and this is 0. So now they do, okay. So this part is shifted left and we end up with 1 over here and 110 unknown over here. The divisor is 3, right? 0011. Since this is less than 3, we don't do anything to u. And we set the last bit to 0. Now, next step, we shift and then we end up with 3. 3 minus 3 is 0. So we set the n quotient to 1. We set this to 0. Then we set the n quotient to 1. And we set this bit to 1. Left shift again. We have this unknown over here. End of the iteration, we have this. So the quotient is this. Remainder is this. Okay. We observe that there can be a maximum of 2 add subtract operations per iteration. It is possible to circumvent it by using another temporary register to store the result of the subtract operation u minus t. We can move it to u only if u minus t is more than or equal to 0. However, this also involves additional circuitry. The u register will get complicated and slower too. The non-restoring algorithm does either one addition or one subtraction per iteration. Hence, it is more efficient even though the asymptotic time complexity is the same. The hardware setup is the same as that for the restoring algorithm. If u is more than or equal to 0, then we subtract. Else we add. U is more than 0. If u is still more than 0, more than or equal to 0, then we set the quotient, then we set the LSB of v, right? Oh, so we are undoing the subtraction in the next iteration. We see that the non-restoring algorithm is very similar to the restoring algorithm with some minor differences. The non-restoring algorithm shifts uv as the first step in an iteration. And if the value of u is negative, it adds d to u. Otherwise, it subtracts d from u. If the addition or subtraction has resulted in a value that is greater than or equal to 0, the non-restoring algorithm sets the appropriate quotient bit to 1, else it sets it to 0. Finally, at the end, v contains the entire quotient. If v is negative, then we add the divisor to u. U will contain the remainder. All right. I'll just skip the proof of correctness part. Floating. So this is 8.4. How much does this say? Is the rest of the entire chapter just on floating point? Let me see. Multiplication, division, summary. Should I read it right now or should I have like a very small stream? Okay, I will take a break and then I will come back. Uh, okay, I will just take a break and then I will come back then. Anyways, see you guys next time. Bye.